When electric current enters a substation panel or an electronic circuit board, and it faces two or more parallel paths, how does it decide how much current flows into each path? Does more current flow through the wire with higher resistance or the one with lower resistance? As an electrical O&M professional, when you are troubleshooting a circuit, knowing exactly how much current is flowing through each individual branch is crucial. That is where the current divider rule comes into play. In this video, we will break down the fascinating working principle behind this rule, look at its core formula, and analyze a practical industrial example to see how it works in the real world. Let us get started. Definition and concept. First, let us look at the definition of the current divider rule, or CDR. The current divider rule is an electrical law used to calculate how the total current entering a parallel circuit divides itself among the various parallel branches. The most important thing to remember here is that this rule only applies to parallel circuits. In a series circuit, the current remains exactly the same at every point, but in a parallel circuit, the voltage across the branches stays the same, while the current splits up. The fundamental principle of this rule is simple. A larger resistor takes a smaller share of the current. This means that whichever path has the higher resistance will experience a lower amount of current. Conversely, the path with the lower resistance will allow a much higher amount of current to pass through. Working principle and formula. Next, let us see how the working principle operates. This rule is entirely derived from Ohm's law. Because the voltage across all branches in a parallel circuit is equal, the current is inversely proportional to the resistance. To calculate this, we use a specific formula. When you have two resistors connected in parallel, the formula to find the current through the first resistor, which we will call IR1, is IR1 equals total current multiplied by R2 divided by the sum of R1 plus R2. Pay close attention here. When we want to find the current flowing through R1, we must place the opposite resistance, which is R2, in the numerator of our fraction. Similarly, if you want to find the current flowing through R2, you would place R1 in the numerator. Practical example. Now let us look at a practical example to make this completely clear. Imagine a parallel circuit where the total incoming current is 10 amps. There are two parallel resistors connected to this line. R1 is equal to 30 ohms and R2 is equal to 70 ohms. Let us apply our formula to find out how much current goes through the lower resistance path, which is R1. IR1 equals 10 amps multiplied by 70 ohms divided by the sum of 30 plus 70. This simplifies to 10 multiplied by 70 divided by 100. 10 multiplied by 70 gives us 700. And when we divide 700 by 100, we get an exact answer of 7 amps. Look at how perfectly the law works. Just as the rule stated, the lower resistance path of 30 ohms pulled the larger share of the current, taking 7 out of the 10 total amps. The remaining 3 amps will naturally flow through the higher 70 ohm resistor. This practical calculation demonstrates exactly how predictable and reliable circuit theory is during field operations. Applications and conclusion. So where exactly do we apply the current divider rule in industrial electrical maintenance and operations? First, it is used in meter shunts. To extend the measurement range of an ammeter, a low-resistance shunt resistor is connected in parallel with the meter movement. This rule allows us to safely bypass the majority of the heavy current through the shunt, protecting the delicate internal components of the meter. Second, it is used in sensor and control circuits. Industrial transmitters often split current signals such as 4 to 20 milliamp loops to drive multiple control panels or recording devices simultaneously. Third, it is highly useful for daily troubleshooting. When parallel loads are acting up, this calculation helps the O&M team determine if a specific branch is drawing too much current due to an insulation breakdown or a partial short circuit. Understanding the current divider rule is an essential step to mastering parallel circuit analysis. If you found this technical breakdown helpful, please hit the like button and share it with your fellow engineers. For more practical industrial electrical O&M content, make sure to subscribe to our channel. Work safely, and we will see you in the next episode.